Okay, well, thanks, Daniel. Hi, folks. My name's Sai,
I'm Moritz.
and today we're going to show you how you can make use of observability in your Swift service. So we're going to start by looking at the core libraries that provide observability APIs across the Swift package ecosystem. And then we'll explore OpenTelemetry and Swift OTel. I'll show you how you can get started with a simple web server demo, and then I'll hand over to Moritz, who will show the benefits of distributed tracing in a larger real-world system. And finally, we'll explain some of the core principles behind distributed tracing, including context propagation and consistent sampling. But before we look at the Swift observability packages, I want to briefly explain the API package pattern that they use. An API package is one that provides only abstractions and no concrete implementations. For observability, this means decoupling the APIs that are used to record telemetry from those that are used to collect and export telemetry. Any non-trivial backend for exporting telemetry will typically be implemented in a separate package. It's then up to the application developer to tie it all together by depending on both the instrumented libraries and a chosen backend. Importantly, this means that the backend specific dependencies required to collect, export, and process metrics are not required by libraries that wish to start using those recording APIs. It means the API package can be free of all dependencies and keep it lightweight so it's ready to be adopted throughout the ecosystem. Those backend dependencies will only be pulled by the application that depends on both the libraries and the backend. So Swift ecosystem has three such packages: Swift Log, Swift Metrics, and Swift Distributed Tracing. You've likely seen these before, but I'm going to give a very, very quick tour of the APIs they offer. So Swift Log's core API is the logger type, and it can be used to log things. There's no surprises there, but the logger API also supports including typed metadata along with each log message. That allows backends to use something called structured logging. And if you want all logs within a given scope to include the same metadata, you can add the metadata to the logger object itself. In this example, the request ID will be included in both of the log messages. So next up, we have Swift Metrics. It typically provides three core types: counters, gauges, and timers. They likely do what you think, but just for completeness. Counters, they count things, which means they produce a monotonically increasing value, but if needed, you can reset them to 0. Gauges, on the other hand, allow you to record an arbitrary numerical value at any time, so that they can go up, and then they can also go down. And timers, well, they're used to record durations, either ones that you've collected manually, or you can use the measure API, which records the duration of a given closure. So finally, we have Swift Distributed Tracing, which allows for the creation of spans. Not those spans that we already heard about before. This span represents a segment of an overall trace through a system. Spans can be nested within parent spans, and each span can have typed attributes applied to it. So to understand how these API packages work, let's consider this example app. It can depend on Swift Log, and so it can just start logging. It may depend on a library, which also uses Swift Log, and there may be other indirect or direct dependencies that all use Swift Log. But where do the log messages go? Well, that's up to you as the application developer to make a process-wide choice of where logs should end up. If you do nothing, by default, they'll be emitted on the console. But if you want to, you can choose and configure a different logging backend. And then you can call Swift Log's Bootstrap API. Now, all the logs are exported to that backend. Not just the logs from the app you collected yourself, but all the logs from all of your dependencies too. And choosing a different backend will affect the destination of all the log messages in the system. So exactly the same principle applies to metrics. Your app and your dependencies can use the recording APIs provided by Swift Metrics. But like before, it's up to you as the application developer to choose a destination. This time, by default, all metrics are just simply discarded. It's like your process is screaming into the void. But if you want those metrics emitted, you must choose a backend package and call Swift Metrics' Bootstrap API. And just like before, choosing a different backend will affect the destination of all the metrics in the system. So by now, you've probably got the drill. Spans, they're created using Swift distributed tracings with Span API, but none of these calls will result in any exported traces. If you want to visualize the flow through your system, you must choose a backend and call the Bootstrap API, choosing a backend that meets your requirements. So because the recording and exporting of telemetry have been completely decoupled, it allows for a diverse ecosystem of backend packages. We have packages for different logging destinations, metrics platforms, and distributed tracing formats, which brings us to OpenTelemetry, because it supports all three. OpenTelemetry, or OTel, is an industry standard and cloud-native project. It provides a specification, which defines an instrumentation API and guidelines for language-specific SDKs. So it's kind of similar to that API package pattern we saw before, but it uses a distinct API. So more importantly for us, it also defines a wire protocol called OTLP for exporting logs, metrics, and traces. And that's what enables us to build SwiftOTel. SwiftOTel is an OTLP backend for Swift log, metrics, and distributed tracing. So it's not attempting to provide the full API or SDK described by the OTel specification. Instead, it's just providing the necessary bits and pieces to export telemetry that's been recorded through those Swift Observability APIs to an OTLP endpoint. It's the format-specific backend for those format-agnostic APIs. It supports both OTLP over HTTP and gRPC. And SwiftOTel's been around for a while. Some of you may have already used it. In fact, it was one of the first backends for Swift distributed tracing. But recently, it's been updated for a 1.0 release. So what's new? Well, in addition to tracing and metric support, SwiftOTel now provides a backend for Swift log, giving it full coverage of those three observability APIs. Next, in addition to updating the existing gRPC exporter to the latest gRPC Swift, which we've heard about today, we now also provide an HTTP exporter. Both of these exporters have been improved and updated, and they now support TLS and MTLS. And as part of the 1.0 release, we took the opportunity to revise the API to make it simpler to configure and bootstrap the observability backends. So we wanted getting started with sensible defaults to be as seamless as possible. So with the new API, bootstrapping Swift Observability is just one line. The OTLP backends do need to perform some background work in order to process, collect, and export that telemetry, but users shouldn't have to care about all the components that make that possible. So this API now returns a single opaque type that conforms to service. All that means is it has an async run method, and you need to call it somehow as part of your process. So you can do that from a task group, or you can add it to a service group if you're using something like Swift for Service Lifecycle. And for the times where those defaults aren't what you want, you can just simply create a configuration object and pass that to OTel Bootstrap. This configuration type is a centralized place to configure all the behavior of the Bootstrap backends. So in this example, we configure SwiftOTel to export traces to a specific gRPC endpoint with a custom certificate enabling compression and using a non-default timeout. But we can use the same configuration type to configure logging, to use the console for local development, say, and to export metrics to a local HTTP endpoint. Let's take a look at this API in action. So I've head over to VS Code, where I've got probably the world's most simple HTTP server. It has just two dependencies, Hummingbird and SwiftOTel 1.0. it has just one request handler listening on /hello and returning just the string hello. It's about as simple as it can get. We do also have a container running locally, this Grafana OTel LGTM container. This provides the OTLP endpoints that we'll use to export our telemetry, and also it's a good way to visualize some of the metrics that are coming from the system. I'll quickly show you what that looks like now before we go any further. So from this drill down section, we can explore the metrics in the system. Right now, it only shows some of the metrics for the internal components that make Grafana work, so none of our metrics are here. If we go to the logs pane, there are no logs here. No logs have been exported so far, and the same is true for traces. There's nothing to see here yet. So let's add observability to our request handler. So I'll start by importing the Swift Observability APIs. And that's enough for me to start using them. So I'll add a log line to our request handler. Here we're using a logger object that comes from Hummingbird's request context, but you could create your own if you don't have one to hand. We can also create a counter, which we can increment for every request. And to complete the trio, we'll create a span. It'll sleep just for an arbitrary amount of time to simulate some work, so we can see it in our trace. So if I head over and run this service, we can start sending some requests to it. And we see some logging in the console, but where's the rest of our telemetry? Well, we didn't bootstrap any backend, so we don't have any. If I head back over to Grafana and refresh, we still don't have any traces, no logs, and these metrics still only contain those metrics for Grafana's own internal components. Let's fix that. We're going to use SwiftOtel today to bootstrap the observability backend, so I'll start by importing SwiftOtel and calling its Bootstrap API. For the purpose of the demo, I'm also going to add a little bit of config to make sure that the intervals at which metrics are exported is much shorter. Now remember, this API returns a type that handles all that background work, that processes and exports the telemetry. So we need a place to run this alongside our HTTP server. Well, thankfully, Hummingbird has an API for attaching other services to its application that should be run alongside all the HTTP routing. So I'll add the observability service to our Hummingbird application. So now if I rerun this service, we can see some diagnostic logging appearing on the console. If you look closely, what it's actually saying is SwiftOtel's taking over the logging backend. It's informing users they're not going to see any more logs coming out of SwiftLog because they're obviously going to be going out of OTLP now. It'll also give you a little hint if you'd like to have a different behavior for local development. So we can send some requests now to this service. I'll send a few. If we head back to Grafana, we should see we've got some traces appearing. This is the span we just created as part of our request handler for our simulated work. We can see the log lines that we added in our request handler. If we head to the metrics pane and refresh, we have this counter that we added. So we've manually instrumented a request handler. And that's great. Wasn't too hard. But really, the benefits of observability come when the whole stack's more observable. So what if we wanted to get telemetry out of all of the requests flowing through this server? Well, thankfully, Hummingbird also integrates with SwiftLog, metrics, and distributed tracing, and it offers those integrations as a collection of middlewares. So with just these 3 lines of code, we can now get logs, metrics, and traces for every request that the HTTP server processes. So I'll rerun the server just one more time, and this time I'll leave some requests running in the background. Now if I head over to Grafana and head over to our traces, we've now started receiving traces for the HTTP request itself. It still contains our span that we created, but this time it's wrapped in a parent span, which has been created by Hummingbird, which contains useful attributes about the HTTP request, including the status code, content length, and even the user agent. This is the curl process that's running in the terminal. And we can even click from here to see the logs associated with this request. Here's the log line from our handler. If we head back to the metrics dashboard and refresh, Hummingbird started also exporting its own metrics about the health of the server, including the number of active requests, and some statistics about the request durations. So let's recap. We've added logging, metrics, and tracing to our request handler, and we bootstrapped the observability backends using Swift OTel. We explored the telemetry using Grafana, and then we added Hummingbird middleware to get even more telemetry with just a few lines. But of course, that was just one service. So now I'm going to hand over to Moritz, who will show us the power of distributed tracing in action.
Thanks, Sai. To kick things up a notch, let's take a look at observability in a more complex system. This is OpenTelemetry's official demo project. It's an online shop made up of a multitude of microservices. It ranges from front-end over shopping carts to payments, all instrumented via OTel. Today, we'll focus just on the cart service, which I re-implemented in Swift. The cart service is called from multiple components. So it gets gRPC requests from the front end and the checkout service. And it also makes outbound HTTP calls to a feature flagging tool. And it uses Valkey to persist and retrieve the user's shopping cart. Most of these components are implemented in different programming languages. However, due to the standardization provided by OpenTelemetry, we can observe them as one shared system. Next, let's go shopping and take the system for a spin. Awesome. This is the OpenTelemetry demo online shop. It's running in Safari. Let's explore what we can see here. It's got a couple of observability tools, so maybe we can check out some telescopes here. I'll go for a couple, maybe 7. Add that to my cart. Let's head back. Binoculars could be useful as well, I guess. Maybe 5. And let's see if there's anything else. Oh, wait a sec, I'm getting a phone call now. Hello, this is Moritz. Yes, I'm kind of in the middle of something. It's about the shopping carts. Okay. Yeah, I'll check that out. See ya. Sorry about that. It seems like our shopping cart is broken, and users can't clear their shopping carts anymore. So let's see if we can reproduce this. So if I scroll back up and go to a shopping cart, I'm clicking the empty cart button, and I'm clicking. Still not working. Huh. Okay, so it's indeed broken. Let's see if observability can help us fix this issue. So I'll head over to Grafana. And this is the dashboard for cart service. So if I scroll down here, I can see that we have 100% error rates on emptying the cart, which doesn't look great. Let me scroll down a bit and see if we can find a couple traces that may be helpful. So here I can see a trace called frontend web HTTP delete. So I assume that's the one that empties the cart, or at least it tries to. So let's check that one out. And it does look like we got a bunch of errors here. Let's check out the span for our cart service. And let's see if the logs maybe help us. If I scroll down here, we can see an associated log. And apparently we switched to an experimental algorithm for clearing the cards. That may have been a bit too rushed, I guess. But yeah, it gives me like roughly an idea where to look now. So let's hop over to VS Code, check out the card service implementation and see if we can fix the issue. So this is the card service. As I showed a couple minutes ago, it uses this awesome single line to bootstrap observability using OTel. Sets up a couple more things, and then if we scroll down, we can see the card service implementation using the simple service protocol that we learned about earlier. And if I scroll down, here we can see we're adding items to the cards, we're getting the cards, and then finally for emptying the cards, looks like we're checking a feature flag called experimental clearing. And then if this is turned on, we literally just throw an unimplemented error. Not the best. Gladly, this is behind a feature flag, so maybe turning that off actually fixes our issue. So let me switch over here and then set the feature flag to false. If we then head back to Safari, fingers crossed, if I empty the card, it works. Thank you, thank you. I wish all these bugs were this easy to fix. Yeah, let's head back to slides to explore how distributed tracing works under the hood. Cool. So now that we successfully fixed the card service, thanks to observability, let's take a look at what makes distributed tracing work. The main thing is called context propagation. Let's take a look at that. So in this diagram, we can see incoming and outgoing requests from the card service, and it receives them by gPC, makes outgoing calls over HTTP. And let's focus on Envoy for a sec, all the way to the left, which is the reverse proxy that exposes our system to the internet. When Envoy receives their requests, it creates the root span of our trace, and thus its tracer generates a unique trace ID and a unique span ID. And the combination of these two is referred to as a trace context, or simply context. It also contains a couple of flags. As part of the forwarded request from Envoy to our front-end service, Envoy's tracer will then inject this trace context into HTTP headers and thus send it along the request. This is referred to as context propagation. Next, our front-end service will then extract the context from headers. It will reuse the trace ID so that we continue the overall trace. It will generate a new span ID, and it marks the span created by Envoy as its parent span. Note that context propagation isn't limited to HTTP, however. So if we follow the flow of our request here, we can see that it's also propagated using gRPC metadata. Observability tools like Grafana can then query all spans associated with a single trace ID and create these beautiful trace diagrams out of it. And this is pretty much what we saw in Grafana just now. Another important feature that's powered by context propagation is consistent sampling of spans. So usually it's not desirable to sample 100% of all your spans, but if we do decide to sample one, then we usually want to sample the entire trace so that we can see the full picture. And earlier I mentioned as part of the trace context, we also have a set of flags. One of those flags is called the sampling decision. And it's same as the trace and span ID, it's also propagated, for example, in HTTP headers. In this example, the envoy span was sampled, and this sampling decision was recorded in the context, and then it's sent along to a front end, and then it goes through the entire system, making sure that everything is sampled. However, in this example, if the root span was not sampled, then we also want to forward that information so that we don't unnecessarily sample any other related spans. Another feature that is powered by the trace context is log correlation. And we saw this in action in both previous demos. And it was what allowed us to jump from traces to logs, and you can also go vice versa. So the way this works is each log line here references a trace and a span ID. And then, again, observability tools such as Grafana can look up all the log lines associated to a span ID or trace ID or the other way around. The trace context is stored inside a task local, and it's used for log correlation in one of two ways. The first one is if you're using SwiftOtel's log handler, then this is built in, you get it for free out of the box. As soon as your log line is surrounded by a span, it will automatically be able to be correlated. However, if you decide to use a different log handler, we still got you covered. You can simply use the Swift log metadata provider included in SwiftOtel. You pass that when you bootstrap the logging system, and then same as before, every log line that happens to be surrounded by spans will be able to be correlated, and this is done by adding metadata to those logs. Okay, let's recap. So I started off with exploring the different observability APIs in Swift, logging, metrics, and distributed tracing. We then exported all three signals via OTLP using SwiftOtel. We used libraries that have built-in support for distributed tracing metrics and logs, such as Hummingbird. In my demo, we also saw Velkey Swift as part of the traces. Recently, work has begun on getting async HTTP clients traced, finally. And then we fixed an issue using observability in a more complex system. And then we finally explored the building blocks of distributed tracing, context propagation, sampling, and log correlation. Here's how you can get involved with observability in server-side.swift. So if you're an application developer, then perhaps just try to bootstrap SwiftOtel or like a different observability system and see what you get out of the box. As I showed, it's pretty easy to get going with built-in middleware in Hummingbird and Vapor. So there's no better time to get started than now. And if you're building such libraries, then also now is the time to implement these fundamental observability packages. So perhaps think about, could you add tracing to your library to make it easier for your users to have observability? And finally, I'd be more than happy for you to contribute to SwiftOtel, be it creating issues or pull requests. A lot of what's been going on for the 1.0 redesign came from contributions from the community. So always glad to see that. You can find Swift OTel on GitHub. We have our own organization there. We're also active on the Swift forums and in the Swift open source Slack. I'm happy to take a couple questions now, but you can also find Sai and me at the lunch break right after this talk. Thanks for listening, and I hope you enjoy your last day of ServerSide.swift.